Alright guys, we're doing lesson 10.8, ending up chapter 8 here, and we're talking about area and volumes of similar solids. And this is actually very similar to what we were doing in chapter 8, so you're going to see me do some references here. But first of all, I want you to think about it. In order for a figure to be similar, they have to have corresponding sides are proportional and the corresponding angles are congruent. So like two equilateral triangles, we knew they were similar because they had the same size, same shape, but the sides were proportional. Any linear measurement was that way. Well, the same thing happens when you're working with similar solids. So when I have similar solids, like two cubes or two spheres, something like that, they say the corresponding dimensions. I want you to think linear dimensions are proportional. So anything with length, they're going to have to be proportional that way. And that ratio of the corresponding linear dimensions of two solids is called the similarity ratio. Exactly the same as we had when we were working with similar polygons. So the same idea happens. We just go from two-dimensional to three-dimensional. So here when I work with cones, I have to check every pair of corresponding linear lengths. We're not going to worry about the angles in this case because lengths are going to actually be the key. So with this, I'm going to do the heights. I'm going to go 8:6. That is 4/3. Then I have the radii, which correspond as 4/3. So my corresponding lengths are proportional, so they're good. So yes, they're similar. And my similarity ratio is 4/3. Now, how did I know how to go 4/3? They didn't tell you, so you have to go left to right. So then the next one, you want to make sure you matchy accordingly. Sometimes they'll even fake it and they'll put the prism on its side so it doesn't look the same. But just make sure shortest sides go together, middle sides go together, longest sides go together. Matchy, and you'll be fine. But you have to check all of them. So I have 7/4. That works. I have 14:8, which reduces down to 7/4. That works. And then I get 10.5:6. So I change that to 105/60. And guess what that reduces down to? 7/4. So is this one similar? Yes. They're similar, and the similarity ratio, going left to right, there's a smaller one here, is 7/4. Now we do the same thing over here with the cylinder. The diameter should correspond, so I get 9/5. My height should correspond, so I go 12:9. Oh wait, that reduces down to 4/3. So no, they're not similar because my corresponding linear measurements are not equal. So no matchy, it doesn't work. So let's go ahead and do the same thing with D. When I'm working with D, we're going to have our heights go together. I get 15:20, and that just ends up being I can't do my math today. 3/4. And then we have our 12:16, and that also ends up being 3/4. So yes, they're similar, and my similarity ratio is 3/4. So it's very easy to check these. So excuse me. So now with that, I need you to go back to chapter 8. I'm going to do it down below here. On chapter 8, excuse me, friends, we learned for similar polygons, the similarity ratio was A to B, the ratio of the perimeter was A to B, and the ratio of their areas is A squared to B squared if I had similar polygons. So now, take that to the next level for chapter 10 with similar solids. Do you think my similarity ratio is going to have the same relationship? I am so sorry with all this coughing. Let me get a quick cough drop while we're doing this. Yeah, your similarity ratio, your linear measurements are still going to be A to B. I'm not going to worry about perimeter, but I still have ratio of area, and that includes surface area, and that's going to be A squared to B squared. So naturally, what is going to be your ratio when you do volume? Yeah, almost all you automatically think it. Oh, that's just A cubed to B cubed. Well, the key with this is you're always going to have to find the similarity ratio in order to change it to the other two. You kind of have to go home when you're doing that. So let's put it into our theorem. Here we have our similarity ratio is going to be A to B. Then the ratio of the corresponding areas, surface area, lateral area would be included, is A squared to B squared, and the ratio of the volumes is going to be A cubed to B cubed. So hopefully that will help us out on the other page. So with this figure, we're going to have to be able to work this out. So I'm going to write the theorem up above. Similarity ratio, A to B, ratio of area, A squared is to B squared. Similarity ratio, A cubed is to B cubed. Making sure I mark the similarity ratio. Oops, that should be volume. Woohoo! Ratio volume. Why did the similarity ratio have to happen twice? Alright, sorry. I've been doing about 4 hours worth of videoing, so I'm kind of loopy right now. So it's probably not the best. But also with this, please make sure that you always reduce ratios before using radicals. This will help a lot on your homework. Let's go through and let's do these together. It says the figures in each pair are similar. I use the given information to find the similarity ratio of the smaller figure to the larger figure. So you have to ask, what ratio do they initially give you if they're not giving you the similarity ratio? Well, here they gave me surface area, which is really the ratio of area. Go left or right again. Actually, they said smaller to larger, so go smaller to larger. So 49 is to 81. Double check, can I reduce? No, I can't reduce, so I'm okay to change it to my similarity ratio. If I have area and I need to go back to similarity ratio, I need to take the square root. So it's going to be 7 is to 9. Now, on B, I look at this, and what did they give us? They gave us volume. So the ratio I should be able to write is volume. So that's 125 to 512. Again, I ask, can I reduce this? And I should have given more examples of reducing than I did, so I'm very sorry. But this one's not reducible, but I gotta go home to the similarity ratio. So now we're gonna do the cubic root. So the cubic root of 125 is 5, and the cubic root of 512 is 8. So it's 5 to 8. Now, how do I do the cubic root not in my head? Well, this is when you have to use your calculator. So hit your math key. Nope, let me turn it on here. And then you go to math. If you go to math, you should see number 4 there. Notice you hit number 4, and that gives you the cubic root. And then you just have to plug it in. What do you get? A 5. Or, so that's 5. And then you do the cubic root again. You hit math, go number 4, and do 512. Enter, should be 8, so it'd be 5/8. So you should be able to get that pretty quickly when you're doing these. Alright, now let's go ahead and actually solve some problems with this. So it doesn't have to use following formulas or surface area formulas. I can actually set up proportions because I know they're similar instead. The surface area of two smaller figures are given. The volume of the larger figure is given. Find the volume of the smaller figure. So this is the larger one. I'm looking for the volume of the smaller one. But I need ratio volumes if I'm finding volume. Notice I only have one of them, so somehow I got to get a different ratio. But I am given surface area. Well, the surface area is really the ratio of area, so I know I can get there. I'm like, okay, I know I have these relationships, so somehow I can get ratio of area to ratio of volume. Well, I have to go home to similarity ratio first. So first, find SR. So if ratio of area to similarity ratio is you're going to take your square root. Get 5, 6. Then I change it to the ratio of volume. So remember, I always go home to similarity ratio, then I change it. Also, I always check to see if that's reducible. It's not, so then I can go ahead and go to my radical. So that's going to be 5 cubed is to 6 cubed, because I have to take my similarity ratio and cube it. So that's 125 over 216. So I set up my proportion. 125 is to 216 is the same as the volume of the smaller one is to the volume of the larger one. Hey, look, they're the same. So therefore, the volume of the smaller one is 125 cubic centimeters. If they're not the same, you just cross multiply and solve that way. So I do the same thing over here for part B. I'm looking for volume again, but I'm given my area. So I use it to write the ratio of area. Cannot reduce my ratio, so I leave it alone. I change it to similarity ratio because I have to go home. Get 4/5. Now I change it to the ratio I need, which is volume. and I end up getting 64 over 125. So now I set up my ratio. 64 is to 125 is the same as the volume of the smaller one is to the larger one. Now I cross multiply. I'm going to divide both sides by 125, and my volume ends up getting, what is 4 times 64? I guess 6. I'll double check myself. My math isn't doing very good here. 64 times 4, 256. I was going right. I just didn't trust myself in cubic inches. Now continue the same process with volume, but instead I have a different starting part. I'm starting with volume, and by the way, cross that out please, but I want to get to surface area. So with these, I look at this, I'm like, okay, what do? I go, all right, I have volume, but I need surface area. So I'm going to work with the ratio they give me first, and then I'm going to change it. So my ratio of volume is 8 to 125. I can't reduce it, so I change it again. I go home to similarity ratio, just like the above one, but I take the cubic root. Now this is when you punch it into your calculator, and you're going to get 2/5. How do I change it to the ratio of area? I take my similarity ratio, I go here, and I square it to get ratio of area. So that's 2 squared over 5 squared. Oh, that's going to be 4/25. So I know 4 is to 25 as the ratio of my smaller one to the ratio surface area of my larger one. So 4 is to 25 as 4 is to SA. So ratio of area, and then I plug in. Oh look, they're exactly the same. So my surface area of the larger one must be 25 square centimeters. Now the same type of process happens for B. I'm given volume even though I want surface area. So I write what ratio I can first, but this time I don't like it because I know I have to reduce it. 5 can come out of both, and I get 8 over 27. Then I change it to similarity ratio, because then I could take the cubic root of 8 over the cubic root of 27 very easily, and that's 2/3. Then I change it to my ratio of area. I square it. 2 squared over 3 squared, that's going to be 4/9. You cannot skip these steps. So when I do this, I get 4 is to 9 is the same thing as 40 is to the surface area of the larger one. A lot of you realize it's 10 times bigger, so go ahead and go SA is equal to 90 after that point. Or you can cross multiply. Divide by 4. Your surface area is going to be 90 square inches. All right, guys, I hope this helps with your notes. And this one's probably the most helpful because it reminds you to reduce your fractions first.